Great. So 20, what a year it was. It's really wild to think about how we started out the year meeting in person, downtown, and now we're doing these virtual remote meetings, which is very interesting to think about how much has changed this year for sure. So we are going to be taking the month of January off. We often will, in our sort of annual rhythm, we often take like July off and then December or off. But so this meeting that we're having today was actually our rescheduled September meeting. So we're having this here in early December. We'll take January off, no meeting. And then our next meeting is going to be in early February. So I'm going to put the link here in the chat so you can see it. And our meeting in early February will be what we've done as our first meeting of the year for the past at least 2 or 3 years, I believe. And that is a meeting of lightning talks. So lightning talks are short 5 to 7 minute talks from you all, from community members. So we're interested in hearing about like something that went well for you, something that didn't go well for you, and how you used R in some project. It can be something that you just learned about, maybe something really interesting and advanced. The idea is to share something about how you used R, maybe a package you learned how to use, how you used R to do some project at your job. These don't have to be super, complete, polished ideas. The idea is for people who are part of our community to have a chance to be able to give a talk. And if you're someone who hasn't given a talk before for a group, it's a really great way to get started. So I would highly encourage you to think about doing it. So since so many things about our meetings have changed over the past year, the way we decided to kind of think about this, it's going to be a remote meeting in February, like a virtual, open to everyone kind of meeting. I know we have a lot of people here who are from the Salt Lake and Utah areas, and then a lot of people who are not, who are from everywhere. And so how we decided to kind of approach this is that the idea of like speaking for our group is open, but speakers who are from our sort of local community are going to be given preference. In past years, we've never had like problems with too many speakers for our like 1 hour slot. And I don't know if we will this year or not, but we really want this to be like our first goal is building up like the Salt Lake City, Utah community with these lightning talks, like who's here, let's give them opportunities to grow their skills in speaking, in sharing their skills. So that's our first priority. So especially if you are here in Utah, here in Salt Lake City, and you have something that you've been thinking about sharing, we would love to hear from you. So if you go to that link, you'll see more info about when it is and a form to submit your topic, your name and stuff, so we can get a hold of you. And so we'll do it like this. We'll have, we'll have you, ask you to share your slides with us, and then you'll share your screen, and we'll, let's just lightning fast go through 5 or 6 people giving talks over the course of an hour. So that is the plan for February. So please sign up. Today, we have my colleague and collaborator, Emil Wietfeldt, speaking. So Emil, I am writing a book with Emil on supervised machine learning for text. And that is the topic of what we're talking about today. We're talking about how about model defaults in R, and specifically with a focus on stop words. So Emil is a data scientist, data analyst at Teladoc, works and lives in Southern California. And I'm really excited to be hearing this talk today. So Emil, thank you so much for coming here and being here. If you want to get started sharing your screen, I think if you all, as we go through this talk, if you have questions, if you want to type them in the chat, we can kind of collect them, and we will go through them at the end.
All right, thank you so much for this kind introduction. So, and as Julia said feel free to ask questions and we will get to them at the end. All right. So what I'll be talking about today is looking at stop words, and more specifically, why you don't just want to trust the defaults in whatever software you're using. So by doing this, let's start to take a dive into one of the fields in natural language processing and subgenres, which is the thought about stop words, which I think for the longest time haven't really been properly explored in the general words we've seen. So let's start with what is stop words. And because this talk would have been very dull if we just have used stop signs everywhere, I've decided to make these set of slides fishy themed, because we're taking a deep dive into the world of stop words. So for some history perspective, we have Hans Peter Luhn, who was one of the pioneers in information retrieval. And information retrieval in that days were a lot of times looking at some text from websites and other things and extracting the information therein, which we now think a lot of people think about as text mining. So looking at your data and finding as much information therein. And he's typically credited with coining the phrase of stop words. He didn't use it specifically himself. That name came about later, and it's a little bit unsure of exactly where it is, but the idea that some words should be stopped when it's being passed through our machinery is something that came from there. That's quite a long time ago now. Probably I would like to think 50s. Maybe not. One of the big issues you have when talking about stop words is the different definitions you're seeing on the web. So I will list the top right here. So in natural language processing, useless words, data, are referred to as stop words. In computing, stop words are words that are filtered out before or after the natural language data text are processed. And stop words are words in any language which does not add much meaning to a sentence. They can safely be ignored without sacrificing the meaning of the sentence. And by looking at these definitions, you start to ponder a little bit, because it gives the illusion that stop words are fairly easy to work with and are more or less without problems. As a matter of fact, many of these sentences I just showed was more or less the only reference to how you deal with stop words in the blog post or article I took them from. So you would have a whole blog post, a whole chapter, and you would generally get between a sentence to a paragraph talking about what you deal with, how you deal with stop words. And the typical consensus is that the easy to deal with, and we remove them, and we're good to go. And I'm here to say that I think that that's not the case. That sadly, the world isn't simple enough that we can just remove these words. So there's a couple of different things that play into why this is a problematic way of handling it. And the first thing we need to think about is what stop words really are. So before we saw that they're being talked about as being useless words that can safely be removed. But it's quite a bit leap to be able to categorize words in some document as either being useless or not useless. And I like to think of them as low information words that contribute little value to the task. And then expand it outwards to be that the different words in some document carry a certain amount of information, and all of that information per word lies on a spectrum, so you are able to more or less rank them. This is a very idealized view, which in practice you can never get close to, but it is too limiting to think of stop words as either being informative or non-informative. You need to be able to think about them in a way where we can start using a threshold. So to this, let's talk about what I kind of mean with word information. So here on the right, we have this visualization that is trying to represent a longer piece of text where each little bars represent a word. And I'll try to talk about what I mean about word information by mapping color onto these rectangles, representing how much information they have. So in the following slides, data colors tending towards purple will be low information words, and lighter colors will be high information words. And the first thing you can think of in a way that information can be distributed over the text is to have a uniform amount of information at each word. First of all, that's not true for most documents. You can have a sentence. You can probably construct a sentence where each and every word contributes the same amount of information, but in practicality, you will get in situations where some words will, just by construction, have less information. You will have some filler words, and you will have, if it's long enough, you will have different parts of the document have different amount of information in them. And also, another point is, if this is true that everything is equally important, you wouldn't even want to think about removing stop words, because any word you remove would be harmful to your prediction model if you're working in a prediction model sense, but it'd be harmful by removing anything. And not on the whole opposite end of the spectrum, you should have completely random information, which is also not how we think about how the world works, because we'd like to think that certain part of a sentence mean more than other parts of a sentence. And here we run into the same problem, that if information truly is random throughout a corpus, then there's no way to figure out what to remove. You see here that basically nothing to do. What we can have, one of the more realistic ways of how information is being represented on a word level in some document, is by having a high variance information, and what I like to call diamonds in the rough. So here we have a document where it's mostly low information words, and here they are represented by like purplish blue, and then once in a while we have a high information word, so there's all the yellows. So we have a handful of words spread throughout that contribute a lot of information, and then everything else more or less doesn't have any information. So this could be one way a document to be structured. In this scenario, we have that only a few of the words have information, but when they do, they tend to have a lot, and most of the words could be thrown out altogether. It's another example right here. Another thing you could think of having is a low frequency amount of information, where we have a smooth transition between the high and low information words. And what we start to see is we have information is pertaining to the location. So we might have, oh, this is a very high information sentence or paragraph. And these two high and low variance informations are both vast simplifications of what we're actually seeing. We're probably seeing a little bit of both. It seems then unlikely that you would have a sentence. So if you look at the top left up here, we have a almost completely yellow sentence. And I think it would be very surprising in English if you would have a whole sentence where every word matters, that there isn't a of or and in there somewhere that just is needed to combine the sentence together. And this is just another added point to make the note that when you talk about stop words, the language matter a lot. And the way the words are being, so I mostly I'm mostly thinking about this using English text. And a lot of these techniques will work across other languages. And English is actually a very easy language to work with, mostly because there's so much data out there that you have so much to work with, but also because the way the English language is structured, most words are separated by white space, and we have very few compound words, which makes a lot of computer-oriented tasks just very easy to work with, because it's very easy just to chop everything by white space. You have all the words in your tutorial, and it's easy to remove what we think about being stop words because they're far and few between, whereas some in other languages, these language features could be combined into other things. So it's just another note to remember that you need to really tailor everything to whatever language you're actually working with. So if you think about words, you should try to list them out as the true information. So here we have a graph, and along the y-axis we have the true unknowable information that the word contains. So that is like absolutely the true amount of information that word carries. And then each bar here represents the first 80 words in this hypothetical scenario. So we see that we have some words with a lot of information, and then it slowly steeps down. I also color-coded each bar according to our estimated information. So if we had a perfect pipeline to analyze this text, you would have a one-to-one mapping between the true information and our estimated information. And then the simple task of removing stop words would just to find a cutoff point and exclude all the words that doesn't have enough information. And you would still have to choose a threshold by figuring out how far along this tail do you want to go. But it's a very easy, if you have a perfect match, you just decide, and it more becomes a computational thing of how many words can my computer handle compared to how much information do I want. And here the problem is because estimating the amount of information is a non-trivial task, and being able to do this one-on-one mapping is highly unlikely. What we tend to see is a more shuffled way. So we have the true information about the y-axis, but the estimated information becomes a little bit more random. We probably have a fairly good correspondence between what we estimated at the high words and they are on the high spectrum. But we will see that some of the words that we estimate as having low information actually have high. And likewise, in the other tail, some of the words that we think, not that important, turned out to be kind of important. And here the problem with choosing a threshold of how many words to include becomes important, because by taking in more words, you have the chance of picking up words that you didn't think was important, but actually was important. But you'd also be unlucky and just hit more actually unimportant words or low information words. Or you could shrink your threshold up to pit a fewer number of words, and you might actually lose some actually true information words. So it's all about a trade-off we have to make. And here the important part is we need to strike some kind of balance between the speed and performance. And performance is actually also quite hard to measure and quantify, and so is speed, because you can have speed in both a computational sense, since that if you remove most of the words, you have fewer words left to work with, so a lot of your machinery might be able to run faster from dimension issues and other things. But it's also a trade-off between how much time you spend working on optimizing the stop word list. And yeah, so it's just something you have to think about. And then with most things in what we're doing, you have to find some balance. And a lot of times it's a speed and performance balance, which becomes hard to walk the line on. So when we talk about stop words, there's mainly three, or there's mostly two ways, but I have a third way, which I think surpasses both the two other ones. But we have main two ways. So the first way is to use a pre-made list. The second way is to just make your own list to fit. And then once I've talked about those, we'll come back to my super secret method, and we can talk about why I think that one would perform better. So when we're talking about pre-made lists, yeah, when we're talking about pre-made lists, so far I've talked about them as being kind of simple to work with. I might even have suggested that there's only a couple of lists out there, and most of them are being well constructed and very handcrafted. And a lot of them are, but both these two traits are more or less wrong. And I'm here to tell you why. So before we really go into the issues with them, we should talk about why you would even start to use a pre-made stop word list. So the pros is it's typically very fast to do in human time. We pit for the list, and you can pit a stop word list in a couple of seconds if you already have it out there. You shouldn't use a couple of seconds, but it's a very fast if you want to do it that way, and it's easy. And a lot of times it's the recommended way in most software documentation and literature. One of the cons is that they tend to be general. And here I mean that they're trying to be able to capture what English is, if you're talking an English stop word list, and that may or may not fit into your specific use case. And I talked before about how we like to think of stop words. Oh, there's probably just a couple of lists out there because fairly easy to do. And that's then not true. So here I have a couple of stop word lists out there on the open web, and we have quite a bit more. And some of these lists are trying to be general, so word general English text. And some of those would be like the Tor, NLP, Sparsy, Scikit-learn, and Jensen. So the list contained in those tend to be fairly they claim to be able to work more or less in most English language because they're trying to be very general. But then you also have some other ones right here. I think the entire one is a metaphor one. Some of these lists are just what they're using internally in their thing. So it might be a keyword optimization thing so that you have different words for that. If you try to make a stop word list that was on a chatting platform, you might have other words that you want to remove because they contain very few information. And one of the issues is all these lists are different, and they're going to be different in slightly different ways. So if you take a look at this poorly drafted sentence I have up here, so we have he got handy. He shouldn't have, but he did. And let's see what words slip through after we remove all the stop words. So here, all the blue words are the ones that are left over after removing stop words. In another way, we can think of all the gray words as the words that appear in the respective stop word list. So here we have the snowball, smart, and LCT stop word list. As you can see, they have slightly different lengths. They're trying to do different things. And here we see that most of the words in this sentence actually disappeared. And in the smart one, we actually only have Tandy left, which would have been surprising if Tandy disappeared because that doesn't seem like it should have been removed. Here we have some more extreme lists. So we have the ISO list, which is a fairly long one, almost 1,300 words, has a lot of different words in it. And if you see it move everything, where the Tor NLP and Talado list together only move one. So the Tor NLP didn't remove anything on this word, where these words don't remove other places. So we can already see here that the choice of list matters a lot, both in terms of length, but also more underlying what words it contains. But here you might think, wait, what about capitalization? So if we look back here, we notice that all the words that I list underneath are lowercase, but the original sentence was uppercase. So the way capitalization is normally handled in an NLP pipeline is doing tokenization. So when you tokenize, a lot of tokenization practices have defaults to turn everything into lowercase. So we drop the case because it can be seen that capitalization isn't worth it in a pipeline. However, this will change the stop word list because the stop word list is just a list of words, which is just a combination of characters, and they only match if they completely match. So if we don't do no conversion to lowercase, then we see that the word he isn't being picked up in the stop word list because it's been uppercase the first two times, but not the last time. And this is true across everything. A lot of stop word lists, and even probably most of them, don't have capitalized versions of the stop words included. So if you don't make sure that the case matches, you might not remove certain words that you were intending to use. And right now I just used the tokenize words function from the tokenizer package to do this tokenization, but there's other ways of tokenizing. And the way you tokenize also has an influence of how the software will run. So here, if we're using a space-separated tokenizer, which is just it takes any white space, that's where it decides to make the cut. then we see that we still keep he because we're also not doing any capitalization transformation, but we also are keeping in punctuation. And in this case, all the punctuation happened right after word with no space, so it's being kept as part of that token. So we have tandy, but it's tandy with a period. And that token in of itself doesn't appear on the list. This token is going to be different than tandy in the middle of a sentence, and it does contain the value that this token has tandy as an end of a word, end of a sentence token, but you lose. But if you don't intend to keep the information, you need to make sure that your tokenizer will match the stop word list. Because if you don't, then you will see have and did being part of your corpus after moving stop words because they are situated around punctuation. Another way to separate everything is you can split on your non-word characters. So we see a couple of things right here. First, we see that the punctuation a couple of places leaves empty strings, which you can probably remove right away if you really want to. But another thing we see is that shouldn't is being split into two because of the accent used to separate N and C. And what we have to see right here is that shouldn't is still being kept in its two part in the snowball and it's being removed in the NLTK, but we're actually losing half of it in the smart stop word list. So what you see is here, it tends to indicate that the NLTK stop word list is being calibrated toward with a tokenizer that splits on non-word characters because it recognizes that this shouldn't word and removes it because it already knows. But if you don't, so here the NLTK stop word list might be a good candidate if you're planning to split on non-word characters. But then you need to make sure everything's compatible. And I think that's what I'm trying to say right here is the tokenizer and stop word list need to be comparable. And I didn't show examples right here, but stemming and lemmatization, which are different techniques of finding the root of a word, which is mostly done by probably chopping off the end, but can sometimes also change the general word. They're changing the words, changing the tokens. And if your stop word list assumes that the words are pre-stemming and lemmatization, then they're not being picked up later on. So one thing that can happen is if you go back here, if we have a system that splits on a non-word character, and then the stop word list include the full word shouldn't as one word, then that part of the stop word list is useless because that token could never appear using that tokenizer. And by looking at the stop word list, you would think that that word is being excluded, but it isn't because it's impossible to actually show up. So it's just very important to make sure that everything's compatible and everything matches. And here we come to like the main part about it is you need to look at your stop word list. And I mean this in the most literal sense possible is in that you want to open up the file, maybe even print it out and just go through each word by word and think about, does this word make sense in the context that we're looking at it in? because some words will be in the list that you don't want it to be, and those should be removed. And we have a thread little note. So if you are using any non-English stop word lists or need a non-English stop word list, there's a couple of situations you need to know. So first, you need to make sure that the list actually works in the language you're trying to apply it to. And this means that a direct translation of an English stop word list will not be sufficient. And I think that there's not if and also but. It will not be sufficient. It's not going to be able to capture everything that happens in the language. And it doesn't, down to the last 2 points, is you need to know about the language you're working with. So if you want to work in Korean, you need to know Korean, or at least enough Korean to understand what's happening. And if you don't, you should hire a consultant that knows the language so you can actually use the language features that you're working with. The same way that if you're looking at information about whales, you would hire a consultant that knows about whales so you can understand why the data is looking the way it is. And it's no different than working with text. So to switch it up a little bit, I'm gonna have a short quiz for the next couple of slides. So if you want to, you can join in the chat. And so go over the chat here so you can see what's happening. And it's a very simple quiz. You will put in so listing 4 different words, and you have to tell me the odd one out. If you want to join, you can join the chat. And this is not meant to be an easy quiz. This is more a quiz just showcasing why stop word lists are messy to work with. So the first one we have right here is with 4 words. We have his, she's, himself, and herself. I'll start a timer. Let's do it half a minute, maybe less. And I would like you to think about these 4 words and type into the chat which one you think doesn't belong. But which one is the odd one out? And it can mean a lot of different things because, as I talked about before, we have something like 80 different lists. And it's a fun problem because what do we really know? And if we move forward, we can see that it's she's. And that's the odd one out, because out of these 4, it's the only one that doesn't appear in the smart stop word list. All the other words don't appear, but all the other words do appear. So we have like a little issue right here. Like, oh, why does she's doesn't appear? And I actually haven't been able to find any documented reason of how this list was constructed. So we actually don't know. Another one. So let's look right here. So we have 4 words: I'll be, Fifi, and system 1. And if you want to, you can join the chat to test which one is odd one out. And if not, it's completely fine. And we'll move over and see what happens. So if we move over, the weird one, the odd one out, is the word Fifi. And this one is odd one out because it was left more or less undetected for 3 years in the default stop word list in the scikit-learn package. And it's a simple misspelling of 50. So a lot of other words, other numbers written as words was included there, and just 50 was misspelled. So if people didn't notice this, they have accidentally removed 50 and not removed 15 or 50. And last one, this one is a little harder. So we have substantially, successfully, sufficiently, and statistically. And these are words, which one's odd one out. And then as you can see, and what I try to do with this notice is think about, why is this an issue? Like, why this shouldn't have been this hard of a question. And what actually happens is statistically it doesn't appear in the ISO list, whereas the other three appear. So we can kind of see right here that the ISO list is a very long list, that it starts including sufficiently, substantially, and successfully, which I would think in a lot of cases could be considered as having some kind of information. And what will happen right here is how these words appear, and you have different generation process. Some of them will be grammar based, so they look through and pick out all the words that would appear in this kind of grammatical structure. You can do all pronouns and adjectives and other word types. And another way of doing it is frequency based. So you can say all the highly frequent words we don't like, and then you can do some more filtering. Some of these are meant to be general, or at least they claim to be, but they might not work in your specific use case. And it's just another reminder is you need to look at the stop word lists before, and I hope this short exercise helps you to see that. And then it comes into nothing. We have that stop word lists will try to be general or domain specific. So a lot of them will try to word with general language. But if you're not working on general language, these lists might not be sufficient, might not work the way you want it to. And a domain specific stop word list will probably not work in what you do. So if you have a finance one, there will be some finance words that mean something very specific in the finance world, then they would in normal way. And if you remove what is considered insignificant in a finance text, in a normal text, you're going to have a bad time because you remove words you didn't want to remove. And the handmade list is the other way of doing it. The longer way of doing it is just you just made the list yourself. And the main ways you can do it is a lot of people use a count-based method. So you just take all the words in your corpus, you order them by frequency, and then you start looking at the top ones and take up the ones that while they appear a lot, you don't feel that they have a lot of information, and you put those on the list. You can use domain knowledge to add what you know won't be important. And then here you have the chance to make sure that the word list actually has everything you want it to. And one of the ways you need to also think about how often the word actually appears, because if you try to make inference about a word that only appeared 2 times in your whole corpus, it's hard to see what actually if it has information or not. Be careful about which word you're using to and how much of what you're actually doing with them. And the seed method is basically just you combine the two. So I would suggest that you start with a services, a smaller list, maybe in the snowball one, and then you add and remove words that you will find appropriate and inappropriate into certain settings. And you get the best of both worlds. You get some of the speed by using a list of very common words that will be used in a lot of different cases, but you still get the finer details of getting your hands dirty and actually looking at all the words. So let's talk a little bit about the different stop word lists. So we just looked at 3 of the beta, or 2 beta and 1 niche text preprocessing engine. So quanteda has the quanteda stopwords function, which is exported from the stopwords function, stopwords package, and that one will default to snowball. The tidytext has the stop_words tuple, which includes a combination of the stopwords from the honest, smart, and snowball. So that one is different than quanteda. So you need to remember that if you try to compare what happens. The tidytext stopword list is longer and will have duplications because each of the stopwords appear more than once if it appears in multiple stopword lists. And lastly, I used in the stopwords from the textrecipes package, I also defaulted to snowball. I personally had some struggles with figuring out how I want, which I wanted. In general, I don't like defaulting to any list because all the lists are wrong, but I ended up on a fairly conservative, well-used one that is constructed dramatically, because the balancing act of pitting a informative stopword list and not informative stopword list is hard to make. And that's why I'm coming in. So we had a lot of talk about stopwords, and we had a little talk about model defaults. So most modeling software will claim to have the defaults. And that's just a fact of life. Everyone thinks that what they made has pretty good defaults. And some cases they might be right, but they might be different than what you want as the user. And they might be different than what you think it did. And this is where the issue comes in, is you might think, oh, it's doing this, but then when you actually do it, it doesn't. And in functions, so here I'm talking about that function specifically now, but the idea kind of generalizes. But we have some arguments that are required and some that are not, and I call these additional. And by having more required arguments, you are making the software less prone to surprises, because you're forcing the user to specify themselves everything that happens. So as long as the functions underneath is doing what is being told, then there's few surprises. But you get a more frustrated user because you're forcing to fill in things that might not change a lot from time to time. So as an example, we can look at the glmnet function, and it has 26 arguments in total, with 2 of them being required. So if you're only filling in the required ones, you just have to give it 2 matrices, and it's required from that, it will fit right there and then. If you're filling in all the arguments, you start by filling in all the different arguments, and some of them, like you have to specify the family, you have to specify, I don't have weights. You have to specify the threshold, the number of iterations in the fitting. And I'm actually lying right here because this is only 19 of the 26 argument. So there's even more you have to fill in. And a lot of people, if a function is built this way, write their own function to pre-fill a lot of these arguments. And what I tend to see is that most software will try to make the number of additional arguments much bigger than the number of required arguments. So because it's a user-friendly thing, very few people would stay using some software that seamlessly put up roadblocks just to be able to do simple things. So let's go through a couple of examples, mostly taking from the tidy model framework. So if we look at step PCA, we can ask, what does it do? I think most of us will say, oh, it's doing PCA, but what does it return? Does it return, and here's a look, I'm meaning once you apply it and you prep it and bake it, how is it transforming the data? And what does it export? All the PCA variables, does it only do some of them? How does it choose it? Does it pick it by the number? Does it do thresholding? And here we have to actually go in to the documentation to see, oh, it's doing it by defaulting to give us 5 components first. And there's no way of knowing this without looking at the function documentation. And that's one of the way the default kind of work in recipes is that most of them will work out the box without having to set arguments. It doesn't mean that they're perfect, but it means that you can get a recipe up and running fairly fast, and then you can modify a lot of things. Another example is from parsnip family. So we do linear wrap, and we can fit it right away. You did a warning saying, oh, you didn't set an engine, but I will default something for you. It's a choice to allow you to fall back on the engine, not having to set it by yourself. But if you're doing nearest neighbor and the same thing, it will error out saying, hey, I'm fine with you not telling me what engine to use, but you need to tell me the specification. So you get into another thing is a balancing act. How much should we assume from the data? And how much do we need to force the user to specify themselves? Another issue that's a little bit related to this is whole naming conventions. But how do we make sure that the same things are called the same things across software and across fields? And it feels that it would be a simple problem, but it isn't, because people might not know other options, or they might not even realize that they're there, and they might not agree that that's the right name for the different things. So here's some of the argument, I think all argument names for boosted tree in R across different different packages, and you see that the names all over the place. Some of them don't have the same. And parsnip is one of the things that parsnip is trying to do is using more understandable names. So you have loss reduction and sample size, but we're still using mtry, which as far as I'm aware, is related to trying m of the columns we have. You can also get into mismatch between names. So along the controversy in the cited language we won't go too much into is the issue between that the logistic regression function does regularization, which a lot of people has very strong views about, and I won't do too much into, but it's an issue between some people think that a regularized logistic regression isn't and shouldn't be called logistic regression. And we tap into the main idea is like, I think you should design your software under the principle of least astonishment, which is when we write the software with the least amount of surprises, and we need to, and likewise, you should use software assuming that the writer doesn't know about the principle of least astonishment. Then for last time, I would like you to, if you word on this, like take a deep look at the stop word list. If you want more resources, there's this great article right here that talks about and looks at a lot of different stop word lists across, like available in Python. I've talked about this and more in the stop words chapter of Julia and I's upcoming book. Then one last time, I want you to look at the stop word lists, and that's it. Thank you very much for coming out. If you want to reach out, here's all my links for everything I have.
Awesome. Thank you so much, Emil. I know we are right at the hour, so those of you who need to hop off, thank you so much for coming. We'll hope you have a great rest of your 2020, and hope to see you in February. Be sure to check out the info about lightning talks and consider signing up. I think, Emil, do you have a little bit of time to take a couple questions
Sure thing.
going over the hour? Okay, awesome. So I think one thing that was brought up early in your talk that you addressed somewhat, but I wondered if you wanted to speak to it anymore, was about uh, differences that we do know about for stop words for different languages. So how important stop words are from one language to another, or what the sort of morphological differences language to language, how it affects stop word use. So are there things we do know about any differences already that we can kind of like sort of pre-existing knowledge we can start with if we're dealing with multi-language data sets or working in languages outside of English?
Yeah, so I think is the point, and a lot of that also just boils down to you need to know whatever language you're working with. If you're working with a more synthetic language, then the idea of stop words become much more challenging because synthetic languages tend to be combined of more multiple words that all change the appearance of a word. So if I remember correctly, Greenlanded languages tend
Yeah,
to have very long words with many, even dozens of syllables in them.
nice.
And that's simply just a structure where each like morpheme in this word affects every other morpheme in the word. So you can have a whole sentence in what we as English think of a word. And but in that case, it becomes really challenging to think about stop words, because if every word affects every other word in the written sense, it becomes much harder for us with using computers to figure out what parts to remove out.
Yeah, yeah, nice. Nice. Does anybody else have a question? If you want to use a little raise hand feature, you can, or you can type it in. Any other questions as we wrap up? Awesome. All right. Well,
All right.
Emil, thank you so much for preparing this talk. And I feel like it's so interesting to be able to like dig deep into a topic that we do so often hear about, like, oh, just here's a sentence about, and here's what to do about this thing, when you're like, oh gosh, is that really the right thing to be doing? So it's really great to be able to dig deep into a topic like this. I appreciate it a lot. So everyone, thank you so much for coming and joining us in this meeting. Have a safe and happy holiday season. And if you're interested in or open to giving a talk with us in February, we would love to hear about your idea for a lightning talk. And we will see you next time. So thank you all so much for coming.